All right, welcome to topic 9.4. In this topic, we are looking at our heating and cooling curves again, but we are now looking at them through a mathematical lens of wanting to determine the total amount of heat involved in the heating or cooling of water. We're going to stay with only water, otherwise we'll have to introduce new constants and we are not going to go about that. So we're going to study this just from the viewpoint of water. So looking at this first graph, we're going to just jump right on in. We have a heating curve. I can see overall it goes from minus 80 to 140 degrees Celsius. Therefore, its temperature went up, thus we're heating it. As we worked on our 9.3 lesson, looking at the overall structure of a heating curve, cooling curve, it's important to remember where our states of matter occur versus where our phase changes occur. So again, anywhere that has a slope, meaning a change in temperature, this is where we have the heating of a phase occurring. As wherever we have a plateau, is where we are just in one state of matter. So from minus 80 to 0 degrees Celsius, with the understanding that this is ice, or water, that it would be ice, being that this would be solid. In step 2, we plateau. So in the second region of this, it's a blend of solid and liquid, and that's because this is where melting is happening. In stage 3, we continue to heat, and this is where it is liquid water. In stage 4, we then blend liquid and gaseous phase, and this is where vaporization is going to happen. And lastly, step 5 is where we are heating the gas, okay, the water steam. The steam or the water vapor is really what I meant to say. Okay, so we have 5 total calculations we're going to do, one that corresponds to each of these 5 regions. We're going to start out with segment 1, which is the heating of the solid, meaning the heating of the ice cubes. We've actually already seen and worked with this equation to find heat, and that is, if you recall, heat stands for Q in an equation, and that's the MCAT equation. So if you look here, it wants to know what is the total heat needed to heat 1 mole of water from minus 80 to 140. Well, we have to backtrack here for a second. M in the MCAT equation is mass, and if we have 1 mole, knowing that the molar mass of water is 18, our mass is 18 grams. The next thing is understanding that this is the solid state here. We have a bunch of constants, and this is the C value, the specific heat value of water when it's in the solid state, because different states of matter react differently to how much heat energy will raise the temperature of a gram of it. Okay. And then lastly, we need delta T. If you recall, delta T stands for change in temperature. It's final minus initial. Well, if our final temperature for this segment was 0 and it started at 80, that means we're taking 0 minus negative 80. Therefore, the temperature change for segment 1 is 80 degrees Celsius. Okay. What I'm going to have you guys do here is just round to whole numbers just to make things easier. So I got 2,991 joules when I crunched that through. Now for number 2, we are now at a phase change. So we have a slightly different way that we're finding Q. We cannot use MCAT because there is no temperature change, and we have 2 phases of matter. We have some solid, some liquid. So we're going to use M times delta H, where delta H stands for the change in the enthalpy, the change in the energy, specifically because of melting. Okay, so we go ahead and plug in 18 grams, and again, we're melting. So this is the delta H that we're going to use, 333 joules per gram. That's pretty easy with just multiplying, and then grams are going to cancel here, So we get that Q is equal to 5994. Excuse me, I'm still trying to get over this cold. So for number 3, we're back to heating, but we're at liquid water using MCAT. Still 18 grams of water, but we're in the liquid state. So that means our C is going to be this 4.18. And this window ended at 100, began at 0, so the delta T is 100 degrees Celsius. So when I multiply that up, I got 7,524 joules. In segment 4, I'm now back to heating a phase of matter, meaning I'm going through a phase change of vaporization. So then I plug in my 18 grams, and my vaporization is this right here. It takes 2,260 joules for every gram of water. And we're going to find that this value is much larger. It's 40,680 joules. So it takes a lot more energy to vaporize a liquid than to melt a liquid. Lastly, we're going to finish heating the steam, or as steam, continue to heat it. 18 grams. We're going to then use this last value here, the 2.042. And then we ended at 140, began at 100, so the change in temperature for segment 5 is 40 degrees Celsius. Therefore, Q is 1,470. It asks, what is the total heat? Well, that means we know the heat involved in each of these segments. So what you need to do lastly is find Q total. And that's just a sum of all 5 answers. Okay, so when we get an answer there, we get around 58,659 joules. Up here, it asks for kJ, which is kilojoules. Well, we know the prefix kilo means 1,000, so 1,000 joules is to a kilojoule. So it's approximately 58.7 kilojoules. And that's how much total energy was needed to convert this ice, 18 grams of ice, from minus 80 all the way up to 140. Here, we found that our Q was positive, and that's because this was an endothermic change, and we were absorbing energy. So I'm not going to talk every aspect out with the cooling curve. I'm going to show you one that's already worked out. So in the cooling curve, we have the same idea. We have 5 steps. We have our gas, liquid, solid, and then we go through our 2 phase changes of condensation and freezing. In this particular problem, we have 36 grams of steam starting at 140 and cooling it all to minus 80. So in segment 1, 3, and 5, we would use MCAT. 36 grams goes in all 3 of these, corresponding the correct specific heat for our 5 different states of matter, or for 3 different states of matter in the 5 segments is what I was trying to say there. And the one thing you'll find interesting is the temperature change is going to be negative, because here we would take 100 minus 140 to get a difference of minus 40 degrees. Here our difference would be 0 minus 100 for a difference of negative 100. And here we would have minus 80 minus 0 for a difference of minus 80. So you find that the cooling curve here ends with all negative values. Okay, so then here we have in step 2 and 4, you're just going through your phase changes. And so with our phase changes here, we just substitute in those values, which again are assigned a negative. Our total, just add them up, divide by 1,000 to get 117, negative 117 kilojoules. The Q is negative. That means it is exothermic and energy then is released.